Good afternoon, everybody. As Andy has said, I'm Paul Garner. I'm a geologist and paleobiologist, and I work as a researcher and lecturer for Biblical Creation Trust. And one of my colleagues is Stephen Lloyd, who'll be speaking to you tomorrow. In this talk, what I wanted to do was address a specific challenge for the biblical creationist worldview from the fossil record, specifically the problem of transitional forms. I want to begin by considering the two contrasting models for understanding the fossil record. So in the middle of this slide, you can see the standard geological column, which represents the rock systems found across the globe and the fossil assemblages that they contain. On the right, you can see the evolutionary interpretation of this geological column, in which the rocks and the fossils represent a record of the evolution of life over long eras of time. And on the left, you can see the creationist interpretation, in which the rocks and the fossils represent snapshots of living things that were buried at particular times in biblical history. And you can also see that in the creationist interpretation, we can divide the fossil record essentially into three parts. There's a part that was formed before the flood, a part that was formed during the flood, and a part that was formed after the flood. And in this slide, I've shown where I think those boundaries should be located, although I should also point out that creationists don't always agree on exactly where these boundaries lie, which parts of the record correspond to which parts of biblical history. But this is the position that I hold. Now, I want to preface the discussion this afternoon of the transitional form question by pointing out that there are lots of things about the fossil record that the creationist model explains very well, often better than the evolutionary model. We don't have time to talk about these things that you can see listed here on the screen in any detail today. But I just wanted to make the point that as we think about a challenge to the creationist model, we need to think about it in the context of the many things that the creationist model explains well, so that we don't get the idea that all of the problems are somehow on the creationist side. So with that being said, let's turn then to specifically the question of transitional forms. And I want to begin by defining what we mean by transitional forms. So transitional forms are organisms that would have developed during the evolutionary transformation of an ancestral group to a descendant group. And from an evolutionary perspective, these transitional forms would be expected to be intermediate in morphology, that is their body form, and also intermediate in their stratigraphic position, that is their position in the rock strata, the rock layers, between the ancestral and the descendant groups. And I think we also need to define the term transitional series, because this is really the strongest form of the transitional form argument. And we're going to look at some examples in just a moment. So a transitional series is a series of fossils where each fossil in the series is morphologically intermediate between the organisms below it in the rock layers and the organisms above it in the rock layers. So in other words, it's a series of fossils in correct stratigraphic order within the rock record, in which each member of that series is successively less like the ancestral group and more like the descendant group. So that would be a transitional series. And if you consult the evolutionary literature, you'll find that there are many examples of transitional series, some of which you may already be familiar with. Some of the well-known examples are listed here. We have the fish tetrapod series, the dinosaur bird series, the whale series, the horse series, and the hominid series, and there are others too. Now, the existence of these transitional forms, and in particular transitional series, is presented as a very strong argument in favor of evolutionary theory. Andy mentioned Jerry Coyne in his opening presentation, and in his book, Why Evolution is True, he says this: the fossil record teaches us three things. First, it speaks loudly and eloquently of evolution. The record in the rocks confirms several predictions of evolutionary theory: gradual change within lineages, splitting of lineages, and the existence of transitional forms between very different kinds of organisms. There's no getting around this evidence, he says, no waving it away. Evolution happened, and in many cases we see how. So I think we need to consider this argument about transitional forms, because it is often used as an argument against our position. And as we think about what we're to make of transitional forms, I want to offer a number of comments by way of response. The first point I want to make is that we should acknowledge that these transitional fossils exist. Sometimes we hear Christians say that there aren't any transitional forms, but I think that's too broad a generalization, and I think any informed evolutionist is going to pick up on that if that's the way that we kind of frame our response. Now, it is fair to say that there are far fewer examples of transitional forms than we would expect given evolutionary theory. Most major groups of organisms do appear abruptly in the fossil record without transitional forms linking them to their purported ancestors. And strangely enough, for the evolutionary model, transitional forms are almost entirely absent among the marine invertebrates, which actually comprise most of the fossil record and would be expected to provide the most convincing examples of transitional series. But it's not right to say that there are no examples of transitional forms and transitional series. So I think we just need to avoid that pitfall and just frame our argument in a slightly more nuanced way. The second thing that I want you to notice is that the terms transitional form and transitional series are interpretive terms. They're terms that only have meaning within the evolutionary model. So in other words, when we use these terms, when we adopt the term transitional form, we are in effect accepting that the argument is already stacked against us. We're already conceding too much, if you like, to the evolutionary argument by using those terms. That the deck is kind of already stacked against us. And for this reason, creationist Kurt Wise, who's a paleontologist, has suggested that creationists don't use these terms as far as possible, and that instead we use descriptive terminology. Now, I recognize that introducing new terminology can be cumbersome, and I'm not expecting that evolutionists are going to sort of adopt our terminology. But I think it is helpful for us to recognize that the term transitional form is a loaded term, and that it's probably best where we can to use alternative terminology. So Kurt Wise has suggested that we refer to these fossils, rather than transitional forms, we refer to them as stratomorphic intermediates. Now, this term stratomorphic intermediate actually combines two other terms. The first is stratigraphic intermediate, which simply means a fossil that lies in the rock layers between two other fossils, and morphological intermediate, which is a fossil that is intermediate in body form between two other fossils. So a stratomorphic intermediate is a fossil which is both a stratigraphic intermediate and a morphological intermediate between two other fossils. And it's these stratomorphic intermediates that evolutionary scientists are then interpreting as transitional forms. So I think we should recognize that there are some examples that we need to address, but where possible, we should try to use non-evolutionary terminology to talk about. But then thirdly, and perhaps most importantly for our purposes this afternoon, we should seek to test the evolutionary claims that are being made about these stratomorphic intermediates. And I want to suggest that one way we can do that is to apply the methods of baraminology. And so I need to say just a few words of introduction about baraminology. Baraminology is the study of the created kinds. The Bible tells us that in the beginning, God created organisms according to their kinds. And the Bible doesn't tell us exactly what those kinds were, but it seems from the clues that we have, both from scripture and from science, that the biblical kind is broader than the modern species and probably approximates what today we would call a biological family. So, for example, all of the cats, the lions, the pumas, the lynxes, the domestic cats, all of those together constitute a single biological family, as do all of the dogs or all of the bears and so on. Now, in 1941, the creation biologist Frank Marsh coined this term baramin, derived from the Hebrew text of the Bible, from two words, bara, created, and min, kind. So this word baramin roughly means a created kind. It's a kind of more technical way of referring to a created kind. And in 1990, Kurt Wise, who we've already mentioned, introduced baraminology, the study of the created kinds, as an explicitly creationist method of identifying the created kinds using a wide range of different criteria that can be applied. And included in the toolkit of baraminology are some statistical methods. Now, I don't want to bamboozle you with statistics, but I do just want to mention a couple of these methods briefly by way of introduction to some of the other things I'm going to say in the talk. One of the widely used statistical methods used by creation biologists is called baraminic distance. Now, baraminic distance is basically a measure of the percentage of character traits that two organisms have in common in order to determine how similar or dissimilar they are. Now, when we refer to characters or traits, we're talking about attributes of organisms that distinguish species from one another. So they're usually attributes of bones or skulls or teeth or something of that kind. So that's one method. And then there's another method called multidimensional scaling, which basically allows those patterns of similarity and difference between organisms to be visualized in 3 dimensions. So essentially what we're looking for when we apply these statistical methods are patterns of continuity between species. In other words, species that have significant statistical similarity to one another, and then species that have that are discontinuous from one another, that show statistically significant dissimilarity. And we interpret continuity between species as evidence that those species belong to the same created kind, and evidence of discontinuity, the dissimilarity, as evidence that they belong in different created kinds. So before we get to look at the transitional fossils, let me briefly illustrate how these techniques work with an example from a very recognizable group of living organisms, the penguins. Today, there are about 18 species of living penguins. They're all classified in the same family, and their nearest relatives in evolutionary terms are birds like puffins and albatrosses. So what results do we get when we apply these statistical methods to the penguins and to their nearest evolutionary relatives? Well, these are the baraminic distance results, and you may find this a little confusing at first, but let me just very briefly talk you through it. It's actually not that hard really to understand the slide. What you can see here, hopefully, are two blocks of species. The one in the lower left, which represents the penguins, and then you have this other block up in the upper right that represents the non-penguins. And if you look at these blocks, you can see that within the block, members of that block are united to one another by significant similarity, statistically significant similarity, and that's indicated by the closed squares. But then you notice that surrounding and separating these two blocks of species, there is statistically significant dissimilarity. And that's indicated by the open circles. So we have two blocks of species, and they have a significant discontinuity between these two groups. The other method that we use is multidimensional scaling. And when that enables us to look at that pattern of similarities in three-dimensional space. And here's what that looks like. So each of the round dots in this slide, each of the colored dots represents one of the species in the analysis. And what you can see is on the left, we have the penguins indicated by the red dots. And then on the right, we have a cluster of non-penguins, which are indicated by the yellow dots. And it's obvious when you look at it in three dimensions that there is this wide gap between the penguins and the non-penguins. So it's pretty clear from this statistical study that the penguins are a separate kind, a separate group from all other birds, including their nearest evolutionary relatives. There is this discontinuity. We can identify the penguins as a separate created group, a separate created kind. Now, it was important to give you that brief introduction because we're now in a position to ask a very important question. What happens when we apply these methods to the fossil species that are regarded as evolutionary transitional forms? And I want to just briefly look at a couple of examples. And I want to look, first of all, at the fossil horses. You may be familiar with the famous horse series. It's often used in textbooks and museum displays as a classic evolutionary series. The series begins with a small creature called Hyracotherium, which has 4 toes on its front foot, and it has low crowned teeth for browsing on leaves. And then a bit higher in the rock sequence, we have this creature called Mesohippus, which was about the size of a sheep, and it had 3 toes on its front foot, and it had low crowned teeth like Hyracotherium. And then a bit higher in the series of rock layers, we have this creature called Merychippus, which also had 3 toes, although the central one bore most of the animal's weight, but it had high crowned teeth for grazing rather than low crowned teeth for browsing. Then a bit higher in the sequence, we have Pliohippus, which is very unusual because some members of the genus Pliohippus have a single toe, the hoof, others have 3 toes. And Pliohippus also had high crowned grazing teeth. And then at the very top of the sequence, of course, we have the modern horse, Equus, which has the single hoof on each foot and high crowned grazing teeth. So we have here a series of fossils that seems to document an overall increase in body size, reduction and loss of side toes, and an increase in the crown height of the teeth. In other words, it's a classic stratomorphic series in the sense that Kurt Wise used that term. Well, in 2003, a group of creationists applied our statistical baraminology methods to the horse series. They included 19 fossil horses in their analysis, including members of all of the 3 recognized subfamilies of horses. And here you can see the baraminic distance results. So as with the penguins that we looked at earlier, the squares indicate significant positive correlation and the circles represent significant negative correlations. And I hope what you can see here is that there are three blocks of species, blocks of positive correlation. They actually correspond to the three recognized subfamilies of horses, but also notice that there are species that correlate with more than one family. So those species connect the three families together into one block of correlation. So what this means is that we can trace a line of continuity all the way from Hyracotherium right through to the modern horse Equus. In other words, it looks as if all of the members of this fossil horse series belonged to a single created kind. And here's what how those species are arranged in three-dimensional space. Notice that there's a kind of trajectory here, a kind of Y-shaped pattern, a Y-shaped pattern with Hyracotherium near one end, and the more modern horses, including the modern Equus, at the other end of this trajectory. And interestingly, the order in which the fossil species appear in this trajectory in three-dimensional space actually matches the order in which they appear in the rock layers. So the authors of this study concluded from these statistical studies that all of the fossil horses belong to a single created kind. And since all of these fossils seem to occur in post-flood rocks, rocks that were deposited after the flood, that this horse series represents the diversification of the horse kind after the horses left Noah's Ark at the end of the flood. And in fact, the biological changes we see in the horse series make sense in that post-flood context, because after the flood, we have evidence that the world was cooling down, and increased body size is can be interpreted as a response to the cooling of the earth. You have a larger volume to smaller surface area through which heat can be lost. The world was drying out after the flood. The world was very wet at the end of the flood, but it gradually dried out. And we see the loss of the side toes, which enables the horses to better be adapted for running on hard ground. The woodlands from the fossil pollen in the post-flood rocks, we see woodlands giving way to grasslands, and we see in the horses the way in which the browsing teeth give way to the grazing teeth. So this all makes sense in terms of diversification within a kind. Now, of course, we're not explaining this in an evolutionary sense. We're not appealing to natural selection and mutation to explain this. This was genetic, latent genetic information that was programmed into the horse kind by God in the beginning to enable the horses to survive and to adapt in a changing world after the flood. But I want then to look at a second and rather contrasting example of a transitional series in the fossil record, the fish tetrapod series. Tetrapods are animals that have limbs rather than fins, and according to evolution, the origin of tetrapods from fish-like ancestors was one of the major events in the history of life, said to be evidenced by a series of fossils found in Devonian rocks around the world. The series begins with fishes such as Panderichthyes that are somewhat tetrapod-like in appearance. They have flattened bodies, elongated snouts. They look a bit sort of crocodile-like. A bit higher in the rock sequence, we have fish like Tiktaalik, which you may have heard of, attracted lots of headlines some years ago. It's an even more tetrapod-like fish with elbow-like and wrist-like joints in its forefins. Then a bit higher in the rock sequence, we have the first appearance of true tetrapods such as Ichthyostega and Acanthostega, but they're very unusual tetrapods because these are clearly aquatic animals. They have limbs that are rather paddle-like and not designed to bear their weight on the land. They're animals that were living in the water. And then a bit higher still in the sequence, we have tetrapods that are more obviously terrestrial, that lack those fish-like characteristics of creatures like Acanthostega. So back in 2018, I was working with a student at the time, and we carried out a statistical baraminology study of the various fossil members of this fish tetrapod series. In fact, we studied 6 different data sets. We don't have time, obviously, to look at all of our results, but I want to show you just a couple of the results that we got, and I'm going to confine myself just to the multidimensional scaling results for reasons of time. So here was one of the data sets that we looked at. Again, each of these dots, remember, represents a different species, a different fossil species. Those that are labeled in blue are the tetrapods, and in the black and the red we have the fishes. And again, what I hope you can see in this slide is that there is a wide gap between the tetrapods on the left and the fishes on the right. There's this discontinuity, a clear gap that indicates that they are members of different created kinds. This is another of the data sets that we analyzed. Again, the same color scheme applies. So we have the tetrapods in blue, and then we have the fishes in red and black. And again, you can see that there are clusters, but between the clusters, there is this gap where there are no fossil species. And so we find that the tetrapods clearly form a distinct cluster from the fishes. And in fact, all 6 of our data sets basically showed similar evidence of discontinuity between even the most tetrapod-like fishes and the most fish-like tetrapods. And this is very important. There was no evidence whatsoever of fossil forms that bridged that morphological gap. There were no fossil forms that filled in that clear, statistically significant distinction between those groups. And so we concluded that the fishes and the tetrapods belong in different created kinds, and that they are not related to one another. Now, this is clearly a very different result from what we found with the horses. Perhaps not a surprise, because when we're looking at the horses, we're looking at species that are all members of one family, probably one single created kind. Whereas when we look at the fish and the tetrapods, we're clearly looking at animals that belong to multiple families and to multiple created kinds. I'll skip over the last couple of slides, because I just wanted, if I had time, just to talk about what this fish tetrapod series really means within the creationist model, because we can actually explain why the fossils appear in this particular sequence, but I think for reasons of time we'll just move on to draw some conclusions. Now, I have put together a reading list which I will link to in the chat. There are obviously other examples that have been studied as well, not just the horses and the fish and tetrapods, but many other fossil series have been studied using the methods of baraminology, which gives us, I think, a very powerful tool to test these evolutionary claims, and you'll find more details in the reading list. So just to sum up, and then I'll close, we need to remember that there are lots of things about the fossil record that the creation model explains well, and we need to evaluate any challenges to the biblical creationist model in that context. But one of the big challenges that we do face concerns claims of evolutionary transitional forms, often presented to us in the media, in textbooks, in museum displays as a very strong evolutionary argument. But as I've suggested in this talk, baraminology gives us now a tool that allows us to rigorously test these evolutionary claims, to test them in something more than just a subjective manner. And when baraminology has been applied to these transitional series, we find that in some cases, the series represent diversification within a single kind after the flood, for example, the horses, whereas other examples of transitional series, such as the fish and the tetrapods, are made up of multiple created kinds. They don't represent genuine evolutionary transitional series. So that's the end of my talk, and hopefully perhaps we'll have some time